Welcome back to elementary statistics. In this video, I want to talk about expected value. The expected value is an interpretation of statistical measures done on probability distributions. So I guess the first thing we need is a probability distribution. I'm going to look at a distribution we looked at previously, the result of flipping 4 fair coins and counting the number that come up as heads. You'll get 0 heads 1/16 of the time, 1 heads 1/4 of the time, 2 3/8 of the time, 3 1/4 of the time, and all 4 coins come up heads 1/16 of the time. We call this a probability distribution, but I mentioned that it can also be called a theoretical frequency distribution. The experiment of flipping 4 coins is one that you can do. Right? You can get coins and you can flip them. Although getting a fair coin and flipping it is technically impossible, we can get really close. Right? Every coin has imperfections and inaccuracies, which leads it to be slightly weighted. Every coin will ever so slightly favor one side or the other. But with a clean, well-manufactured coin, the difference is negligible enough that we can ignore it and mostly consider the act of actually flipping a coin to be the theoretical flip a coin that we talked about for this distribution. And so, in that experiment of flipping a coin, we know everything that could possibly happen. And we've listed out everything that could possibly happen in this probability distribution. That means that a theoretical frequency distribution describes a population. And so if we're going to talk about a population, we will talk about some of the population characteristics, like the mean, which you can get by adding up all the scores and dividing by n. When we looked at a population as a frequency distribution, we found that it was very convenient to multiply each possible score, each unique score, by the frequency at which that score occurs, and we found that it was convenient to find the total number of scores in the distribution by adding up all of the frequencies. In a probability distribution, instead of having a frequency, you have a probability, but it serves the same purpose. So I can just replace frequency with p of x and get an equation that works quite nicely. Although I can't even take this one step further, because remember that a probability distribution is defined so that every outcome of the experiment is represented exactly once. And the probability that an outcome occurs when you perform an experiment is 100%. So the total of all the probabilities will always be 1. You can simplify things a little bit, and you can calculate the mean by adding together all of the x times p of x values. Right. I think I have enough space here. Let's slide this frequency table over, or I guess probability distribution table over, so that I can introduce one more column, x times p of x. All right, 0 times 1/16 is 0. 1 times 1/4 is 1/4. 2 times 3/8 is 6/8, which reduces to 3/4. 3 times 1/4 is 3/4. 4 times 1/16 is 4/16, which also reduces to 1/4. Very convenient in this particular probability distribution that everything ended up with a denominator of 4. So I can calculate the mean of this distribution by just adding together 0 plus 1/4 plus 3/4 plus 3/4 plus 1/4. All told, that is 8/4, and 8/4 reduces to 2. All right, so the mean of this distribution is 2. And when we talked about mean, it wasn't too much longer before we also talked about standard deviation. Again, I'm talking about a population, not a sample, so I'm using sigma for my standard deviation. Remember, in general, that's the square root of the sum of all of the x minus mu's squared divided by n. And as with the mean, when we were calculating standard deviations, we found that it was convenient to take, instead of all of the x's, take all of the unique x values, subtract the mean, square them, and then multiply by the frequency of that x value. And then we find the number of samples by adding up all of the frequencies. And here, once again, a probability distribution is a frequency distribution that just replaces frequencies with probabilities. So I can rewrite this as the sum of all of the x minus mu squares times p of x, all divided by the sum of p of x. And once again, the sum of all p of x is 1, so this simplifies even further and is just the square root of the sum of x minus mu squared times p of x. Continuing through this, I find that it's useful to think about where some formulas come from. So we can go through and do some algebra on this formula. It doesn't take all that much. If you get a little bit lost along the way, that's okay. The final result is the only thing that's really important. But I want to show you the algebra just to stress the idea that in mathematics, and statistics is an applied mathematics, in mathematics, nothing is just invented out of thin air. It all builds off of something. So this formula that's behind my head right now absolutely does work, but it's kind of tedious to use. And it turns out that using the ideas of probability to our advantage makes a much easier to use formula available to us as well. To show you how that works, I'm going to expand this out, and it's going to get really messy. So again, if you don't want to copy this down, if you just want to follow along, that is perfectly fine. But it should make sense in that every step should be reasonable algebra. I can expand out. X minus mu squared is x squared minus 2 times x times mu plus mu squared. All of that's still being multiplied by p of x. And I can distribute so that I'm adding together all of the x squared times p of x minus 2 times x times mu times p of x plus mu squared times p of x. The next step is a little bit messy, but it's actually just a nice property of addition. Remember this sigma sign, the summation symbol, means add all of these things together. And I can add them all together like this, or I can add together each piece separately. The sum of x squared p of x minus the sum of 2x mu p of x plus the sum of mu squared p of x. And then I can factor some things out. When you're adding a bunch of stuff together, let's see, x changes with each term, p of x changes with each term, but the 2 and the mu are the same in every single term. So I can factor those things out. And at this point, we get some really good things happening. Remember, the sum of x times p of x is exactly what we mean by mu. And here's one we've used a couple of times. If you add together all of the p of x, you get 1. Right? So this thing simplifies really quickly, really nicely. We have the sum of all of the x squared p of x. Unfortunately, there's no getting rid of that. And then we have minus 2 times mu times this summation, which we said is just another factor of mu. And then we have mu squared times, well, 1, which is just mu squared. And if I have a minus 2 mu squared and I have a plus mu squared, then I can just do some combining like terms and get minus mu squared out of it. And we have a shortcut formula for calculating the standard deviation of a probability distribution. Right. Again, you could use the original formula for standard deviation. It absolutely works. Nothing has changed. But if you know this shortcut formula, then you can use it much more readily, much more rapidly. And again, if you got lost a little bit in the derivation there, if it wasn't all that clear to you, that's okay. The important thing is that we came to this, and the whole point of the derivation is just to show you that it's not just magic. It follows the rules of algebra, and the definitions of these things happen to work out in a coincidentally advantageous way to give us this nice, simple formula. All right, let's get back the same probability distribution we've been working with. Remember from what we saw before that mu in this case is 2. And then start building out the variables that we need to use this formula. We need not just x, we'll also need x squared. So if I go through and I square each of these, right, each of the x values, so 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. And then my formula says I need x squared times p of x. So I take my p of x and my x squared and I multiply them together. 1/16 times 0 is 0. 1/4 times 1 is 1/4. 3/8 times 4 is 12 over 8, which reduces to 3/2. 1/4 times 9 is 9/4. Unfortunately, it does not reduce. And 1/16 times 16 is 16 over 16, which reduces to 1. All right, now I need the sum of x squared p of x, which means just add all of these things together. 0 plus 1/4 plus 3/2 plus 9/4 plus 1. I guess I can find a common denominator of 4. Right? I'm not even going to bother writing 0 because 0 plus anything is that thing. But 1 plus 6 is 7, 7 plus 9 is 16, 16 plus 4 is 20. So I have 20 over 4, and 20 divided by 4 is 5. All right. So going through all of that gives me that variable in the formula. Right. The formula has scrolled off the screen, so let me rewrite that sigma is the square root of the sum of all of the x squared times p of x minus mu squared. The sum of all the x squared p of x is the 5 that's right here. Mu is 2. 2 squared is 4. 5 minus 4 is 1. And the square root of 1 is 1. So my standard deviation for this distribution is 1. For the next example, I want to go to a different distribution to finally explain what is meant by expected value. Right? Sometimes it's called expectation value depending on the sources. Expected value is slightly more common. Mathematically, we write the expected value of a random variable, e of x, capital E, evaluated at the random variable x. And it is simply the mean of the distribution, which immediately brings forth the question, why do we give it two different names? The answer for that is entirely one of interpretation. When we talk about the mean of a distribution, we are talking about a single point on the distribution. When we're talking about expectation, we're talking about an interpretation of the distribution. But it mostly comes down to the same thing. The expected value of a distribution asks the question, if you do the experiment often enough, what are you going to see happen on average? Often enough is an idea that I don't want to try to define in this course. That's a really messy concept in statistics, and it's what separates statistics from much of mathematics. But we can have this idea of often enough, and we can think about it, and we can use that to make predictions about the future. A classic example of expectation value is a lottery problem. And I really shouldn't try to write and talk at the same time. I know better than that. But I'm going to look at a lottery game that is kind of boring. There are two possible outcomes. Either you win or you lose. And of course, they aren't equally likely. If you have ever played the lottery or even looked at a lottery game in real life, you know that most lottery games have intermediate prizes. So you can win the grand prize, you can win a secondary prize, or most of the time you still lose. To make the math simple, we're looking at a lottery where you either win or lose, nothing else can happen. Right. In this particular lottery game, it costs you $5 to purchase a ticket. And since it costs you $5 to purchase a ticket, the value of losing is negative $5. If you lose, you're out the money you spent on the ticket. In this particular lottery game, if you win the lottery, you win $5,000. But that's not $5,000 in your pocket because you're still out the $5 you spent on the ticket in the first place. So you're really only up $4,995, right? The last $5 is what you spent to buy the ticket in the first place. And it turns out in this lottery game, you have a 0.0001 chance. As a percent, that's 0.01%. 1/100th of a percent is the probability that you are going to win. And the rest of the time, 0.9999, you are going to lose. So if we take our x values and multiply them by p of x, 0.0001 times 4,995 is 0.4995. And 0.9999 times negative $5 is negative 4.9995. And then to calculate e of x, which is the mean, remember that's the sum of x p of x. Did I have to write out all this? No, but just a reminder. These things all mean the same thing. You can call it the expected value, you can call it the mean, you can call it the sum of this column. They're all the same thing. But we want to take 0.4995 and we want to add negative 4.9995. And when we do that, we get negative 4.5. As an expected value, we're saying that on average, you spend $5 on a ticket and you're just going to be out $4.50. Of course, practically speaking, you're never out $4.50 on one ticket. You buy a ticket, you spend $5. You usually get nothing back. Every now and then, you get $5,000 back. In a problem like this, which we use a lottery problem as a classic example, I want to mention that this is also one of the most important ideas in actuarial science. If you think about an insurance policy, it costs a certain amount of money to buy an insurance policy. Most of the time, you buy an insurance policy, nothing happens, and you're out the money. Every now and then, you buy an insurance policy, you get into a car accident, your insurance policy pays to replace your car. So usually you're out the $300 or whatever your insurance policy costs. Every now and then you're up $12,000 because your insurance policy just bought you a new car. Mathematically, it's the exact same thing. And so, if I get out of the way of it, often the thing that we really care about on these problems is positive or negative. If the expected value is negative, that means that you lose money most of the time. If the expected value is positive, that means you earn money most of the time. In the case of insurance, it's very important for the insurance salesman to look at this. And they have to look at it as I gain money positive when somebody buys a policy. I lose money negative when I have to buy somebody a new car. Because an insurance person has to earn money, otherwise they'll go out of business. Right. As a discussion point for this problem, or for this video, I want you to think about that idea of expectation. I've given you two classic examples. And do you know of anything else, anywhere else in your life where the idea of expectation might be important? Have you come across something where knowing the expected value might be something that would have helped you make a better decision, or something that you want to make sure that you look into to make sure you're making a good decision later on? Right? In any event, that's all I have on this video. So thanks as always for joining me. I'll see you next time.